Alright, so in this video we go over the third part of hypothesis testing. So we are going to test this time a claim about the mean, but in this case in which the standard deviation from the population is unknown. Alright, so in this case it is S that we are going to use, which is the sample standard deviation. This test is going to work in a very similar way as that of the previous one, in which we knew the standard deviation from the population. So the assumptions are the same: sample, simple, random sample, and these two conditions are satisfied. Population normally distributed, or the sample size is greater than 30. If you look at the formula is very similar. However, what's the difference from this formula and the previous one? Here we use the letter T instead of the Z, and here we use the letter S instead of sigma, which is the standard deviation. So T comes from the T distribution. We already learned about this when it came to confidence intervals. Or in this case, we call it T-score. We call these T-scores instead of Z-scores. And S, again, it was already pointed out, sample standard deviation. All right, the same criteria if we reject the null hypothesis, we reject the whole if the test statistics falls within the critical region, the shaded region, okay, and we fail to reject otherwise. What are the calculator commands that we are going to use this time? Well, so we are going to use instead of in Z, we're going to use int, and in this case we are going to use the alpha value and the degrees of freedom. Keep in mind that for the T distribution, we don't use a sample size, we use degrees of freedom, which is the sample size minus 1. So, and the p-value, we don't use normal CDF, we're going to use the TCDF. Again, we use lower comma upper, and then we specify the degrees of freedom. So the best way is just to go ahead and look at the corresponding examples here. Okay, so let's look at the first example. So a researcher claims that houses in a particular community average less than 90 days on the market. Alright, as a random sample of 9 homes average 77.4 days on the market with a sample standard deviation of 29.6 days. Assume the population is normally distributed, which is good to know, because if you look at the sample size, it's just 9. That's a lot less than 30, but we have the other condition. The population is normally distributed. So test the company's claim at alpha equals 0.05 significance level by comparing the calculated t-score to the critical t-score and comparing the p-value to the level of significance. All right. So let's see. Again, let's write our given information. Well, big N, which is the population size, we don't know, and we don't care as usual. We know the mean. So the mean, which is what's claimed, 90 days, and the standard deviation of the population in this case is unknown. We don't know sigma. However, we take a sample from here. We take a sample and our n equals 9, which in terms of degrees of freedom, that's 9 minus 1, which is 8. Okay, and our mean of the sample will be 77.4. Well, which clearly it's less than 90 days, but again, this doesn't mean anything. We need to have statistical evidence, not just numbers. And the standard deviation of the sample of 29.6. All right, so this I'm going to put it in a box. Okay, so that's the information about our sample. All right, so in this case, well, alpha equals 0.05. That means 95%. Means 95%. Okay, and in this case, well, let's state, before we shade the region that we want to work with, let's state the null hypothesis and the alternative hypothesis, that is the whole and the half. Okay, in this case, well, we read the word less than 90 days. Well, less than, not less than or equal, or at most 90. So in this case, this is less than, doesn't include the endpoint, doesn't have the equal sign. So in that case, they're giving us the ha. Okay, the alternative hypothesis, which is the mean being less than 90. Okay, greater than or equal 90. Okay, that's the opposite logic, you know, that's the logical opposite of mu being less than 90. All right, now let's calculate the critical value. Well, before finding the critical value, observe that this is less than, so this is going to be a left-tailed test. So this alpha equals 0.05. It's going to go here towards the left. Okay. So we need to find the cutoff value denoted TC, that is the T-score critical. All right, T-score critical. And how are we going to find that T-score critical? Well, again, we're going to use not the inv norm, but rather the inv T. And in this case, of alpha, degrees of freedom. And then, well, let's put numbers, inv T of alpha, which is 0.05, and the degrees of freedom, which is 1 less than the sample size, which is 8. So let's go ahead and use our graphing calculator. Well, so I'm going to go never mind. So second distor, and we're going to put the inv T. Inv T area, that's 0.05, degrees of freedom is 8, and all we do is just paste. All right, and we get negative 1.85.95. Just the same way for z-scores, the rounding rule for t-scores is also 2 decimal places, so negative 1.86 will be our cutoff value. Okay, that's going to be 1.86, negative 1.86. Okay, so that's our critical value. Everything smaller than this, we're good, we have enough evidence, and we reject the null hypothesis. Otherwise, we get a number larger than this, we fail to reject. Calculate the statistic. Well, T equals sample minus population again, and then the standard deviation of the sample. Notice I'm using lowercase s as opposed to sigma, lowercase sigma. So let's put numbers. That's 77.4 minus 90 divided by let's see, divided by 29.6 by, in this case, the square root of 9, the sample. Notice it's n itself, not n minus 1. All right, so in this case, using a calculator, we get negative 1.28 as our test statistic. And if you notice, negative 1.28, it's going to fall right here in the non-shaded region. T equals negative 1.28. For this reason, again, let me here reject the null hypothesis, and here fail to reject the null hypothesis. So in this case, because we fell into the unshaded region, we fail to reject the null hypothesis because there is not enough evidence to support our claim here, which corresponds to a type 2 error. Type 2 error it is. All right. So in this case, well, now let's do it using the p-value. So we are going to use the TCDF distribution, and then, well, because we are on the negative side, I'm going to put a negative big value and to negative 1.28. So negative big to negative 1.28, and then degrees of freedom, which is 8, that's one less than the sample size, right? And then let me show you how do we get this. So we go to second dister, and it's, if we scroll down to number 6, that's where TCDF is. So negative big, I'm just going to type negative 9999. Whoops. And then upper negative 1.28 degrees of freedom equals 8. And paste. Negative, so we get 11.1182, which rounds to 0.118 to 3 decimal places. Now let's put this together with the significance level. Well, in this case, alpha is 0.05 and p is 0.11.8. So in this case, this number is way bigger than the significance level, and this is the reason. This is why we fail to reject rather our claim. Okay, so let's look at another example. So looking at another example, well, let's see. An auditor claims that the average annual salary of a project manager at a construction company exceeds. So the auditor in this case, it's saying it's doing its research, or the auditor is the researcher. So in this case, exceeds. It doesn't say that is at least $82,000 because, I mean, again, when we interpret this and we state it into a logical sentence for the alternative or null hypothesis, the fact that it exceeds, it doesn't say it is also equal to 82,000. So that's going to be very important when we look at the wording. A random sample of 20 project managers. Well, look at sample size is less than 30. Well, hopefully the salaries are normally distributed. We'll find out. And had an average of $89,600, which is clearly above 82,000, with a sample standard deviation of 12,700. Assume the salaries of the managers are normally distributed. Indeed, normally distributed. Otherwise, if we don't read that the population is not normally distributed, if we don't have that known, and if our sample size is less than 30, that means we don't meet the conditions to perform the test, and the test will be invalid. So we need to test the company's claim at 0.01 alpha significance, and by comparing the t-scores with and p-values. Okay, so, well, in this case, let's population size, the population of all auditors, we don't know and we don't care. Their claimed mean salary is 82,000 with a standard deviation that we don't know. All right, we don't know. So in this case, well, take a sample and of n equals 20, which in degrees of freedom is 20 minus 1 equals 19. And x bar, which is the sample mean, 89,600, and s equals 12,700. So that this is our sample, information. Well, in this case, alpha equals 0.01. That means a 99% precision test. All right. So in this case, well, let's from here, from our first sentence, the auditor claims that the salary exceeds. So exceed means to be greater than. The who, the ha. So the mean is greater than 82,000, and it for the null hypothesis we are going to state its logical opposite, which is less than or equal 82,000. So let's see, in this case, because of the direction of the inequality sign, that means it's going to be a right-tailed test. So what are we going to have? This is going to go over here, shade the region to test, and in this case the T critical, not the Z critical. We're looking at T scores this time. So, well, we will find out what that is. So in this case, well, to calculate the critical value in T, that is 0.99. In this case, we are at 0.99 with degrees of freedom 19. Okay, so let's see. You might want to just copy the inf T and replace the 0.05 with 0.99 and replace the 8 with a 19, close parentheses. So, and we get 2.54. Keep in mind to round to 4 decimal places. Okay, so let's see. I mean 2 decimal places, not 4, 2.54. I was reading the 4. 2.54, so that's 2.54. Okay, if we get anything bigger than 2.54, then we reject the null hypothesis. Otherwise, if we get anything here in the unshaded region, we fail to reject the null hypothesis. All right, so let's perform the test. So in this case, T, not critical, that's just T. X bar minus mu divided by S over the sample size. And in this case, that's 89,600. Well, I'm going to omit the comma here. Never mind. Minus 82,000 divided by 12,700, which is the standard deviation of the sample divided by the sample size, which is the square root of 20. And using a graphing calculator, I get the value of 2.68. All right, so let's compare our statistic value with our critical value, and in this case clearly 2.68 is larger than 2.54, which lies within the shaded region, that is T equals 2.68. And for this reason, we have enough evidence to reject the null hypothesis. So there's enough evidence to support our claim. And a possible type of error, error 1. We already discussed all about types of error. If not, you can look at the previous video. Let's compare the p-value with the significance level. Well, TCDF of this 2.68 in this case, because we are going to go from 2.68 all the way to some big number, basically infinity. Well, we're not going to type infinity. We just call it big number. And the degrees of freedom has to be specified. All right, so in this case, the CDF, well, I'm going to do the test again. The CDF, and that's 2.54 to big number, and degrees of freedom in this case is 19. Enter 0.099, basically 0.010 if you want to round it. 0.010. So putting together P and alpha, so P value is 0.010 and alpha is 0.01. All right. Okay, be careful here. And in this case, this is less than or equal. In fact, these two numbers are equal. So this is why we reject the other way to verify that we reject the null hypothesis. Let's look at a third example. Example 3. Well, a risk. So what do we have for number 3? So a researcher claims that the average cost for a family of 4 to attend a Major League Baseball game is not equal to $172. Is not equal. Well, that's our alternative hypothesis. That's where we're going to get this the information to state it. So a random sample of 22 families reported an average of 189.30 cents. Well, and 34 cents. Well, that's clearly not equal to $172 with a sample standard deviation of $33.65. Assume that population is normally distributed. Well, in this case, because our sample size is just 22, not larger than 30, but well, we have that population is normally distributed, the population of people that attend a Major League Baseball game. All right. So test the company's claim at an alpha 0.05 significance level, which is actually 95% precision test. All right. So in this case, well, let's state the population size. Well, big N, that we don't know and we don't care. We don't need to know. Mu, the mean of the population, is 172, and sigma is unknown. All right. So let's see. So n equals 22 with degrees of freedom of 22 minus 1 equals 21. The sample mean equals 189.34, which is the sample mean, okay, the mean from the sample of 22 families, and their standard deviation S is 33.65. Well, in this case, well, because we have that's the ho, that's the ha. So the mean is not equal to 172. And its logical opposite is the mean being 172. All right. So in this case, well, because we have a not equal sign on the alternative hypothesis, well, this is going to be a two-tailed test. So this alpha 0.05 will be alpha over 2 of 0.025 on the one hand and on the other hand as well. Alpha over 2 equals 0.025. So Let's shade. And we are going to find a T critical, a lower value, and an upper value. In this case, we don't need to find both, because if I do 0.025, in this case, that is second vars for inf t. In this case, I want the area of 0.0 0.025, oops, 0.025, the degrees of freedom, which is one less than the sample size, that is 21, okay, and paste. Takes a few seconds to calculate. Well, I'm gonna get 2.07, that's 2.08, negative 2.08. So inf t, let's calculate. 0.025 and 21. So that's what did I get? 2.08, negative 2.08. So negative 2.08 below and positive 2.08 above, because the distribution, just like the normal distribution, the t-distribution is symmetric. So we get negative values and positive values here. And again, shaded region, reject the null hypothesis. Otherwise, fail to reject. All right. So let's calculate the test statistic. Well, so I have t equals sample minus population over s over the square root of n, and in this case is 189.34 minus 172 divided by s, which is 33.65. That's the standard deviation of the sample, divided by the square root of the sample size, which is 22. And using a calculator, here we get 2.42. Okay, so now let's compare these. Where is this 2.42 landing at? So this 2.42 falls within the shaded region. All right, falls into the shaded region, and in this case, this means that we have enough evidence to reject the null hypothesis. So now let's do the calculation using the second method, using the p-value method, using TCDF of 2.42. In this case, big, because it's towards the right. So start at 2.42, go all the way to something big. And then the degrees of freedom, don't forget, 21. And let's see. So I'm going to do second dister TCDF. So 2.42 upper, which will be, what's the upper? Something, just something big, and degrees of freedom, 21. So we get 0.12, rounding to 3 decimal places. So if we put together the p versus the alpha, 0.012, and alpha, which is 0.05, clearly this number is bigger than that. All right, so that's why in this case we are good. The shaded region for the statistic part does not exceed that of the standard cutoff. All right. And in this case, because we reject the null hypothesis, there's a possible type 1 error. Okay? Alternative hypothesis win, possible type error 1. And let's do one last example. This very last example is what I call a special case. Okay? Why is this a special case? Because the z-test is stronger than t-test. What do we mean by this? Because, well, you may be given on an exam, on a quiz or something, you may be given a situation like this, okay. So an insurance company claims that the average automobile on the road today is less than 6 years old. A random sample of 15 cars had an average age of 5.4 years with a sample standard deviation of 1.1 years. All right. Assume the population is normally distributed. Well, because look at the sample size is very small. With a standard deviation of 0.9. Well, in this case, we are given two standard deviations. We are given the standard deviation of the sample and we are given the standard deviation of the population. Well, keep in mind that in statistics, ultimately, we want to make estimations or test hypotheses from data from a sample and possibly to know a little bit about the population. Well, when we don't know anything about the about the population, well, we have to use the t-test. We don't know the sigma from the population, that is the standard deviation from the population. But in this case, we know both of them. We know the sample and we know the population standard deviation, because we know this. In this special case, and I'm going to highlight, we're not going to do t-test. We are going to do the z-test, because we know at least one parameter from the population. So in this case, choose the z-test. So when you are given a problem like this, be careful with the given information that you are given. So in this case, population size, we don't know, we don't care. The mean, which is 6 years. The standard deviation, which is known, in this case is 0.9. All right. And we take a sample of n equals 15. In this case, no degrees of freedom, because we are going to use the z-test, not the t-test. And the mean of the sample, that's x bar, which is 5.4. And the standard deviation, well, is given the standard deviation of the sample. I'm going to write it down, but at the same time I'm going to cross it, because we are not going to need it. We're not going to use this piece of information. So is less than 6.5? Well, it's going to be, when we state the ho and the ha, the ha will be that mu is less than 6. And then its logical opposite, mu greater than or equal 6. All right, let's make this look like a 6. So, well, if alpha 0.0 is equal to 0.05, well, that's mean 95% precision. And then look at the direction of the inequality sign. This is going to indicate that it's going to be a left-tailed test. shade the region. All right. Well, in this case, it's going to go all the way here. In this case, we're not going to use the T critical. We're going to use the Z critical because you're using the Z test, not the T test. Okay. So let's find the critical value. So in this case, well, inv norm of 0.05. And we write the 0 and the 1 when we type it in the calculator. Let me show you again. So in this case, second distur inv norm 0.05. The 0 and the 1 are going to be there. Don't mess with those. Paste and then click enter. Again, keep in mind that you can erase that 1, delete that 1, the comma and the 0, and just have this. Okay, you still get the same value. 1.64, negative 1.64. So our critical value is negative 1.64. Calculate the test statistic. Well, so we're going to use the formula, the other formula, the old formula, Z equals x bar minus mu divided by sigma over square root of n. So in this case, well, I have 5.4 minus 6, and sigma, which in this case is 0.9 over the square root of 15. Okay, this calculation, I don't have it in my on my notes. So in this case, I'm gonna show you how to do it. Open parentheses, 5.4 minus 6, close parentheses, divide by, open parentheses, 0.9 divide by second square root of 15. Oops, delete this, go outside of the radical, close parentheses. And I get negative 2.58. So I get negative. Now let's locate this value, negative 2.58. So negative 2.58 is clearly a number less than negative 1.64. So Z equals negative 2.58. All right. So, well, look at this value, look at this area. Well, so it's smaller than the standard area. So in this case, there is enough evidence to support that we can reject the null hypothesis. Now let's do it using the p-value. We use the normal CDF. So in this case, it's negative big to 2.58. Okay, and then you will see the 0 and the 1 that you can always delete it from the calculator. Okay, so let me show you that again. So normal CDF, so negative big, negative 2.58, 0 and 1, don't change those, and click enter. If you want to delete that 0 and that 1, 0.049. Okay, so 0.05 I get. So 0.005. So that's our p-value, and that's our alpha, which is 0.05. Clearly, this is larger. Okay, so actually the other way around. That's smaller, not larger. It's larger in the number of zeros, but not a larger value. My bad. So less than or equal, less than or equal. Okay, so again, so this last example covers one of these special cases in which we need to be very careful about the information that we're given. In this case, you may be given both standard deviations, that of the sample and that of the sorry about that, and that of the population. So in this case, if you know something about the population, the standard deviation of the population, go with that. And as opposed to the t-test, use the z-test, which is what we did here essentially. Alright, so I think this is a good place to quit, so let's call it a day. I will see you on the next video.